So in number 26, we have a space habitat for a long space voyage. It consists of two cabins, each connected by a cable to a central hub, as shown. The figures are set spinning around the hub axis, which is connected to the rest of the spacecraft to generate artificial gravity. A. What forces are acting on the astronauts in one of the cabins? Well, the correct answer is it would just be a normal force acting this way. That would be the force of the floor pushing in on the astronaut, which would feel like gravity to them. B. Write Newton's second law for an astronaut lying on the floor in one of the habitats, relating the astronaut's mass, his velocity, his radial distance from the hub, and the normal force. And in this case, they're writing normal force lowercase n. We're going to write it our standard way, F sub n. So for part B, F net equals ma. In this case, what's the net force? Well, it's just going to be that normal force, which is equal to the centripetal force. Remember, centripetal force is the net inward force, which we know is equal to mass times centripetal acceleration. In this case, we want to calculate it in terms of velocity and radius, so we simply would plug in v squared over r for centripetal acceleration. And literally, that's all you would need to write for part B. C. What would the normal force have to equal if a 60 kilogram astronaut has experienced half his normal Earth weight? Well, plugging it in real quick for C, we just need to figure out half of his normal weight of gravity. So mg divided by 2, which is going to be about 294 newtons, half of the weight they would experience on Earth. D. Calculate the necessary tangential speed, regular velocity, of the habitat from Newton's second law. So for D, using that same equation we derived back in B, and now plugging in our numbers. We need the normal force to be 294 newtons, the mass of our astronaut 60, and the radius is 10 meters. Solving this one, you'll discover the velocity or tangential velocity just about 7 meters. E. Calculate the angular speed from this tangential speed. Well, if you remember your conversions back from the Rosetta Stone, omega times r is equal to v, or you can rewrite it as omega is equal to v over r. In this case, our velocity is 7 meters per second from the previous problem. Our radius is 10 meters, and so you'll discover our angular velocity is 0.7 radians per second. F. Calculate the period of rotation from the angular speed. Well, if you remember, one of the equations for angular velocity is just 2 pi over t, or you could calculate from velocity as well, but I'm going to use this one, easiest one to work with, because we know omega and we're looking for period. In this case, plugging in our numbers, we get that, and if you take 2 pi divided by 0.7, you'll get a period of almost exactly 9 seconds, 8.97 seconds to be more precise. G. If the astronaut stands up, will his head be moving faster, slower, or at the same speed? Notice they're asking for speed, not angular velocity, as his feet. The answer is it would be slower. Omega is the same, but speed, which is talking about the magnitude of the velocity, is going to be smaller. Why? His head is covering less distance, a smaller circumference, in the same amount of time as his feet. Finally, calculate the tangential speed at the top of his head if he's that tall. Oh, actually, I think I labeled this one H, but in reality, it's still part of G. In this case, I'm going to use the reverse of the one I used in E. Velocity is equal to omega times r. In this case, omega we know is 0.7. The radius of his head is now going to be 10 minus 1.8. Or 8.2 meters. And if you multiply that out, you'll discover his head's only moving this fast. Notice that this is smaller than the velocity of his feet, meaning his head would undergo less centripetal acceleration. Would it be comfortable? The answer is no. It would feel weird. His feet will feel heavier than his head, and yeah, it would not be a very comfortable feeling. It would not be ideal. You don't have a difference in acceleration between the two. I hope this helped.